So far, all of our discussions have been about one collinear field. When we do SET, we actually, in general, want to talk about more than one collinear field. So how would we generalize everything we've discussed to more than one? So we would have, in this case, more than one energetic hadron, more than one energetic jet. So far, we've been talking about one energetic hadron or one energetic jet. What if we have two jets? Then we would need two types of collinear field, one for each of those jets. And basically, what we have to do is take our collinear Lagrangian. Well, let me call it Ln0, which is the fermion piece plus the gluon piece. And we sum over n. We have to sum over all n's, which are corresponding to individual distinguishable collinear fields. So the question is, what does it mean, sum over n? What is the distinction between collinear fields? And so here's the words, and then we'll explain what they mean. This sum is over inequivalent n's. Well, that should be obvious that they have to be inequivalent. But what makes them inequivalent is the fact that they are RPI equivalence classes. So that's a funny sentence. Inequivalent RPI equivalence classes. So two n's are the same if they belong in an equivalence class that could be connected to where they could be connected by reparameterization invariance. So you should think of the n's that I'm summing over here as just members, one of each class. They're the kind of just picking out what that class is, just labeling it by one member, and then I sum over an inequivalent set. So let's just imagine that we have some n's, n1, n2, n3, and we can ask the question, what makes them equivalent or inequivalent? So let me call them that the Ni collinear modes for any I are distinct if, and there's a condition, that if I dot two of these n's together, they should not be close together. And in fact, that they should be some value that's much bigger than lambda squared. Obviously, if I was equal to j, we'd get 0. But for any I not equal to j, we will say the n's are inequivalent if the dot product is much bigger than lambda squared. So let's see why it's lambda squared by doing an example. So that's, if you like, how you can define the equivalence classes. Let's imagine you have some momentum p2, which is a large piece times n2. And then you dot n1 into it. So n1.p2 is q n1.n2. And that would be of order lambda squared if n1.n2 were of order lambda squared, right? But if n1.n2 are order lambda squared, and therefore n1.p2 is order lambda squared, you would say p2 is an n1 collinear particle, because this is the right power counting for an n1 collinear particle. So it's both n1 collinear and n2 collinear, and that just means n1 and n2 are just two members of the same equivalence class. So if this is true, that the dot products of order lambda squared, then n1 and n2 are within the same equivalence class. Which, if you wanted some notation, you could say n2 is in the class defined by n1. So you could really think of this as a sum over classes, but I guess usually people just write sum over n. OK, so that is in some sense clear that you want to be summing over things that are distinct. In this case of back-to-back jets that we talked about, they're pretty distinct. One's going this way, one's going that way. the n's dotted into each other are 2, so that's certainly much greater than lambda squared. But in general, this is what you have to have in order to make them distinct fields. So then everything basically that we've talked about kind of goes through again. And I'm not going to dwell on it, but I will just kind of repeat some things. So collinear gauge transformations, for example, you would have now a new type of scaling that you can have for different fields. And you could have 2 different types of collinear gauge transformations, one for your N1 collinear fields, one for your N2. If N1 and N2 are distinct, then those will have distinct scalings for the corresponding momenta, so they'll be distinct transformations. And fields won't transform under the other guys. N1 collinear fields won't transform under the N2 gauge transformation, because again, that would spoil the power counting for their momenta. So at some level, it's very intuitive to figure out what the results are. I'm not going to go through it, but suffice it to say that we would have collinear gauge transformations for each collinear guy. Reparametrization, same story. We have separate invariances for each pair of n's. So n1 and n1 bar. For the n1 sector, we have a reparametrization symmetry. n2 and n2 bar for the n2 sector, reparametrization symmetry, etc. And here is actually where you see that there's something kind of that looks different than Lorentz invariance that's going on, because the reparametrizations are only acting within a sector. So if you do an N1 type reparametrization, there's no transformation of an N2 type Wilson line or an N2 type gauge field, right? So an N1 transformation affects the N1 collinear fields and objects, N2 type, which could affect that. And it's more like a Lorentz transformation that sort of acts within the sector all by itself, but it's not really a Lorentz transformation. It's this reparametrization symmetry. Okay? But it's exactly the transformations we wrote down, just you don't transform N2 type fields when you do an N1. And just like we had before, if you do matching calculations, you get Wilson lines, but now there can be more than one type. So we had this W Wilson line that showed up when we did matching calculations, and I want to give you here one example, which we'll come back and talk about more later on, and which we've already mentioned. So consider our example of E plus E minus producing 2 jets. So in the full theory, you just have a vector current from the photon. And if you want to match that onto the 2-jet operator, you can go through the same type of thing that we did when we were doing the beta S gamma example. And the difference is here that we get 2 different types of Wilson lines. So this N1 Wilson line, Wn1, my notation here is that the subscript is supposed to indicate to you that it's N1 bar of AN1 that shows up, and then likewise Wn2 is a function of N2 bar dot AN2. Okay, so you have to decide whether you're going to call it W sub N2 bar or N2, but anyway, this is my notation. So you get Wilson lines that are built out of the N1 bar dot AN1 fields, which are order lambda 0, or the N2 bar dot AN2 fields, which are order lambda 0. So this is lambda 0, and This is lambda 0. Okay, so by power counting, we can certainly get objects like that. And when you go through the process of integrating out off-shell particles, just like we did for beta S gamma, where we attached gluons and we found that some lines were off-shell, so we had to integrate them out. If you do that for this process, you get this operator. So when we construct the effective theory, we have to integrate out off-shell particles, and by doing so generates this Wilson line operator. It's a little more complicated in this case because we get these two Wilson lines. And I'll talk a little bit more later on in a different context about kind of what type of diagrams are involved in getting these two different Wilson lines. But the result is, in some sense, more intuitive than the way of getting there. What's happening is you're getting this Wn1 Wilson line next to the Cn1 field, and then this form of combination here is gauge invariant under the N1 collinear gauge transformations. And the same thing here. This guy doesn't transform under the N1 collinear gauge transformations. This guy does, so this guy's invariant. This guy's invariant under N2 collinear gauge transformations. They both transform under ultrasoft gauge transformations, so they get connected in that way. And again, you have sort of, if you just think about gauge symmetry and how it should come out, then you would have guessed that it should be this. But you can also derive it this way. Yep.
So for the one collinear sector, it's been very top-down. Is this when you start to throw in many sectors? Would you?
So you could.
Like,
so this is the top-down way of thinking, that you just generate it by integrating out, and you can do that. You know, do it to all orders of the tree-level diagrams. That's possible. Or you can, but we're starting to see a picture emerge from the bottom up, right?
Right. I'm talking about the top order. So that's pretty bottom up only. Is there a way of, because you're like saying, okay, let's sort of state that the effective theory has, you know, mini copies of the collinear gauge.
So
gauge fields.
Right. So I mean, you could try to think, you know, of writing a formula, right? You could try to think of it like, let's take A and let's write A. Let's just do 2, right? You could start trying to do that, but at some point it just loses its friendliness. It's not really buying you anything. So starting to think from the bottom up is actually a good way of going at this point. You could still do it from the top down, but it just gets more and more cumbersome. Any other questions? All right.